FJ and FCJ. FCJ we are getting it from the PN sequence. Okay, PN sequence generator. So in the spread spectrum techniques, we know very well that we'll be using the PN sequence. So here what we are doing, we are dividing the PN sequence into segments. Okay, segments of like 2 bits or 3 bits or 4 bits or 5 bits. Like that we are segmenting and we are giving it to the frequency synthesizer. So based on that segment, whatever segment I have, like if I'm dividing it into 3 bits, so you can just see an example here 000. So this 000 will be given to the frequency synthesizer. So this frequency synthesizer will provide a frequency for this particular segment. So that I am representing with FCJ. That is given to the mixer. Okay, so FJ and FCJ are the frequency components which are input to this multiplier. So what it will do, it will multiply both of them. And this is not FJ into FCJ. It is not FJ into FCJ. See, here I am saying that this frequency component is input to the multiplier. It means that it will be like, you remember like for your BPSK signal, we were representing the modulated signal as root 2 EB by TB. Written somewhere, I think so. Somewhere I've written. Okay, anyway, I'll just show you. So the modulated signal output, if you just recall, the modulated signal output is given by root 2 EB by TB cos 2 pi F1T. So this is what the frequency, this F1, I'm saying that this is FJ. Okay, FJ is nothing but F1 in this, or root 2 EB by TB cos 2 pi F2T. Okay, so this is what the second frequency in case of BFSK. Okay, so that is what is the input to the multiplier. Okay, so multiplier will get this. This is nothing but cos Fj. Here also it will be cos Fcj, something like that. So that is given to the multiplier. So by using the trigonometric functions, you'll be able to expand it so that in the expanded term you'll have Fj plus Fcj and Fj minus Fcj. And here this two components should be passed through the bandpass filter. So here we need to tune the bandpass filter in such a way that it will take only the some component in this is Fj plus Fcj. That will be the output. Okay, so this is all related to the transmitter. In the same way, you have the receiver. Okay, so receiver, first what I need to do, I need to despread the data. So since I want to despread the data, again I'm using the same PN sequence generator. Whatever PN sequence generator I was using at the transmitter, the same I should use at the receiver end as well. So the received signal will have Fj plus Fcj, and since I'm using the same PN sequence generator and the frequency synthesizer, I'll get Fcj. So multiplication, again I'll have two components at the output, the sum of these two and difference of these two. Okay, again here what I need to do, I need to tune the bandpass filter in such a way that I will be able to pass only the different signal. Okay, why only the different signal? Why I don't want this? Because this see, the output of this, I should have only Fj. Fj is nothing but the modulated signal frequency. Only that should be available at the output so that I can demodulate this easily. Okay, so that is the reason. Otherwise, in the some component you will have Fj plus 2 Fcj. So it has got an additional term as well. Okay, so what I need to do, the bandpass filter should be tuned in such a way that it will give me only the difference output. Okay, so difference output is nothing but this. So if you just observe here, Fcj and minus plus Fcj and minus Fcj will get cancelled, and I'll be left out with only Fj. That Fj, that signal is given to the demodulator. So the demodulator, what it will do, it will give me the binary data. Okay, so here it is nothing but the reverse operation of the modulator, what you are doing here in the transmitter. In the transmitter, we are modulating it. So the same thing, see, Fj is the output. Now what I'm doing, this Fj, I'm giving it to the demodulator so that I'll get the binary data. So the reverse operation is happening at the receiver end. So Fj is given to the MFSK demodulator, and I'll be getting the binary sequence. Okay, so here so here I'm using an additional carrier which is coming from the PN sequence through the frequency synthesizer. Okay, so using this, I am saying that I am spreading the sequence. Okay, so this FH is this frequency hop spread spectrum. It is divided into two types. Okay, so the first one is slow frequency hop spread spectrum, and the second one is fast frequency of hop spread spectrum. So first we'll see what is the slow frequency of spread spectrum. See, frequency by using the FSK techniques, you are spreading the incoming data. Okay, but here it is happening slowly. Okay, slowly this the variation in the frequency is happening. Okay, so that is the reason it is said to be the slow frequency of spread spectrum. So you may ask me a question, how we are able to say it is slow. Okay, so for that, what I have done, I have denoted some notations here. Okay, so what is that? TB is nothing but the bit duration. If TB is bit duration, then RB is the bit rate. Okay, so inverse of the bit duration will give you the bit rate. So that is what I have taken here. TS, symbol duration. This is what the symbol duration, symbol rate. This is the chip duration, and this is the chip rate. So here the chip duration or the hop duration both mean the same only, but the difference is, like in the, if you take the spread spectrum, direct sequence spread spectrum, we were taking only one bit as TC, but here you're dividing it into segments, right? So the transmitter, and what you're doing, you're dividing it into space segments like this. So this complete segment, okay, these 3 bits or 4 bits, or how much ever bits you're segmenting, all these bits together is your TC. The duration of this 3 bits is nothing but TC. That is what the difference, you need to note it down. Okay, so here chip duration or hop duration both mean the same. So chip duration, if I have chip duration, it is nothing but chip rate. Chip rate is RC. Again, it is nothing but 1 by TC or 1 by TH. Both mean the same. Okay, so this is what the notations. Okay, so here I am saying that it is the slow frequency of spread spectrum. It means that the symbol rate is less than the hop rate. Okay, symbol rate is less than hop rate. Okay, it means that the hop rate is hopping rate in the sense hopping means, as I've already mentioned, it is nothing but the shifting from one frequency to the other frequency. Okay, so here the hop rate is less than the symbol rate. Okay, it means that the symbol rate is more than half rate. Okay, hop rate. Okay, so the same thing I have represented in the form of equation here. So in the slow FHSS, what happens is the symbol rate is greater than the hop rate. Okay, what it means is, in one okay, let me write the same thing, same in the different way, so that you will understand what it is exactly. Okay, so what I'll do, I will just cross multiply. So I'll have as 1 by Rs, which is equal to n into 1 by Rh, which is equal to, I'm just taking this to this side and this to this side. So 1 by Rh is equal to n into 1 by Rs. Okay, 1 by Rh is nothing but Th or Tc. Th, which is equal to n times Ts. Okay, so, or I can even write it as Tc. Tc is equal to Th. Okay, here we can, I will be able to say that in one hop. Okay, so let me consider one hop in the sense, like one shift from one frequency to the other frequency shifting. So in one hop, I am able to transmit this many symbols. Okay, one hop, I am able to transmit this many symbols. Okay, so here the hop rate is less than the symbol rate. That is why this is said to be the slow frequency hop spread spectrum. So this we will understand by using one example. Okay, so note down the question. Okay, now let us note down the question. To understand, see here I have just stated it. Okay, what I have stated, the symbol rate is greater than the hop rate, or the hop rate is less than the symbol rate. This is what I have just stated here. Okay, the hop rate is less than symbol rate. Okay, so the same thing I have expressed in terms of equation. See, Rs is greater, and this is Rs will be equal to n times of Rh. Okay, now the same thing I can represent even in terms of duration, time duration. Okay, so here if you just observe, TH is nothing but the hop duration. TH is nothing but the hop duration. And TS is nothing but the symbol duration. So the hop duration is greater than the symbol duration. What it means exactly is, in one hop I will be able to transmit multiple symbols. Okay, that's what it means. Let me consider th is equal to 2ts. It means that in one hop I will be able to transmit two symbols, 2 times of ts. This indicates two symbols. Okay, so that is what will happen in the slow frequency hop spread spectrum. So that is the reason it is called as slow FHSS. Okay, this we will try to understand with one example. Okay, in the exam also, if they ask you to explain related to slow frequency hop spread spectrum, then you have to write all this, like from here you can start, and here only you can mention RH is hop rate, RS is symbol rate, and TH is hop rate, and TH is hop duration, and TS is symbol duration. Like that you can just mention. Okay, so all this you need to write with example. Okay, so now let us write the example. Okay, the question is, if 4-state LFSR is nothing but linear feedback shift register, whatever we have seen before. Okay, if you just recall, in the PN junction, PN sequence generator, I'll just show you the diagram. Here in the PN sequence generator, we have used this C3, C2, C1, C0, and C1 and C0 will be given to the modulo 2 adder, which is nothing but the XOR gate. Okay, so this output will be fed as feedback to C3. This is nothing but LFSR. Okay, so if they ask you to explain PN sequence generator using LFSR, this is what you need to explain. Okay, so that is what he is mentioning here. Let me just go back to the problem. If 4-state LFSR with initial state, as I've already mentioned, if you just recall, except 0, 0, 0, 0, it can take, since it is 4 states, I have taken 4 outputs here. Okay, 0, 0, 0, 0. Except this, you can take any combination from 0, 0, 0, 1 to 1, 1, 1, 1 as initial state of the LFSR. Okay, here he is specifically mentioning you take it as with initial state as 1, 0, 0, 0 as shown. Okay, in the sense here he is giving the LFSR circuit as well. If they don't give you, you can draw it on your own. C2, C3, C2, C1, C0. All these are nothing but the flip-flops. Okay, and here we'll be taking the output sequence, which is nothing but the PN sequence. So C3 to C2, C2 to C3, C1 to C0. C0 output along with C1 output, it is fed as feedback to like you have to XOR between C0 and C1, and you need to give it as feedback to C3. Okay, so here this is nothing but the XOR gate or modulo 2 adder. Okay, so this is what the circuit given. Okay. Okay, and here he has mentioned number of bits per MFSK symbol is 2 and length of PN sequence length of segmented PN sequence is 3 find the first one, period of PN sequence. So here we'll get the PN sequence. So he is asking you to find the period of that. Next B, PN sequence of one periodic length. One periodic length. Third one, assume carrier hops to a new frequency after transmitting 2 MFSK symbols. 2 MFSK symbols, or he may also mention as 4 information bits for the binary sequence. Here he is giving the binary sequence. He is given as, for the binary sequence, 1 0 0 0 1 1 0 1 0 0 0 1 1 1 1 1 1 0 0 1. This is the binary sequence given. Binary sequence which is nothing but the input to the modulator. Okay, we input to the modulator. Okay, next fourth one, here only this is what he has given. Sketch hopping frequency versus time. This was the first problem. The third one. Fourth one, I have represented as D. Also sketch D-hopped frequency versus time. Okay, so this is what the question he has given. So here what we need to do, I will just explain you. First he has given the LFSR. He is asking you to define the PN sequence, find out the period of PN sequence. Why we need to find? Because it is periodic signal. Okay, PN sequence is periodic, so we need to find the period of that. Then in one period, what is that PN sequence, that we need to find. Then here he is saying that the carrier hops to a new frequency after transmitting 2 MFSK symbols. Okay, so here if you just recall, I have represented something as RS is equal to N RH, or I have even represented it as TH is equal to NTS. Okay, so what he is mentioning, see the hopping. Here he is mentioning that a new frequency, assume carrier hops to a new frequency after transmitting 2 MFSK symbols. It means that the TH or TC here will be equal to 2 times of TS. In the sense, the after transmitting two symbols, then only it will hop to the next frequency. That is what he has given. So that is the reason TC is equal to 2 TS. Okay, so that we will use here. Okay, and he is saying that it can be either 2 MFSK symbols or 4 information bits, because when m is equal to 4, here he has also mentioned something related to this also. What is that? See, number of bits per MFSK symbol is 2. It means that each symbol consists of 2 bits. Okay, and length of the PN sequence is 3. Segmented PN sequence. See, here I have mentioned if you take the transmitter, I have mentioned that we need to segment it. Okay, so each is segmented with 3 bits. Okay, so that is what he is mentioning here. Okay, so let me just write what he has given and what we need to calculate. Okay, so first let us go to the solution. Okay, so first one, given, let me write as given. First, whatever he has given, let us write. Okay, so number of bits in bits per symbol is 2. Okay, next, number of bits in segmented PN sequence is 3. Okay, so since I have 3 bits segmented, so 3 bits in the sense I may have any combination as 0, 0, 0 or 0, 0, 1 until 1, 1, 1. So I need to have how many frequencies here? See, take the transmitter. Here the PN sequence is segmented to 3 bits. So since it is segmented to 3 bits, I should have 8 frequency components. So 8 frequency components to spread the spectrum. Okay, so I need 8 sequence like this. So I will write the same thing here. So number of frequencies required to spread the signal. Is 2 power this n value 2 power 3. It is nothing but 8 frequencies I need. Okay, so it will be from 0, 0, 0. It is FC1, 0, 0, 1, FC2, 0. Okay, let me start from FC0. Okay, FC0, FC1, FC0, 1, 0, FC2, 0, 1, 1, FC3, 1, 0, 0, FC4, 1, 0, 1, FC5, 1, 1, 0, FC6, 1, 1, 1, FC7. Okay, and here he is saying that we are dividing the number of bits in a symbol is 2. It means that k value is given as 2. So if k is equal to 2, m will be equal to 2 power k. It is nothing but 2 square. 2 square is 4. So I need 4 FSK sequence here. So again 0, 0 can be represented as F0. Let me take as F0 only. 0, 1 I'll take as F1. 0, 1, 0 I will take as F2. 1, 1 I'll take as F3. Okay, so if you just take the transmitter, this Fj is nothing but F1, F0, F1, F2, F3. In the same way, if you take 3 bits, if you segment PN sequence with 3 bits, then Fcj is nothing but you will have Fc0, Fc1, so on until Fc7. Okay, so these are the frequencies that will be given to the mixer like this. Okay, so before going that, first we'll take the first part of the question. See, here I have just represented what is given, and from the given terms I have derived few things. Okay, from the given terms I have derived few things. Now I'll go with the first part of the question. Okay, so this is again the repetition. So you have the sequence C3, C2, the same thing. First I need to generate the PN sequence. C1, C0. This is what the given. Here I'll get the PN sequence. Okay, and here I'll give it to the modulo 2 adder, and from there it is fed back. And he's saying that the initial values of the flip flops is 1, 0, 0, 0. Okay, so 1, 0, 0, 0 is the initial outputs of this flip flops. Okay, C3, C2, C1, C0. Okay, and here this C0 is nothing but it will indicate the PN sequence as well. C0 output is nothing but the PN sequence also. PN sequence output is nothing but C0. Okay, so this is what it is. So now what I need to do, C3 is nothing but C1 XOR with C0. Okay, so 1, 0, 0, it will be like shifted. It will shift for each clock pulse. It will shift. So you will get as 1, 0, 0, and this 2 will get odd, and I'll get the value here 0, 0. It will be equal to 0. 0 XOR with 0, it will be 0. You know the truth table: 0, 0, 0, 1, 1, 0, 1, 1, 0, 1, 1, 0. This is what the truth table of your XOR gate. Okay, so 0, 1, 0, 0. Next, this 0 will come here, 1, 0. These 2 will OR, and I'll have the value like this here. Okay. Next.
Swapna madam.
Sir. Good morning, sir.
Which module?
Last module, sir. 5th module. Last module, last topic, sir.
Okay. Please continue.
Okay, sir. Okay, so this 0, 0, 1 will be shifted towards this side. So 0, 0, 1, and here these two will get XOR, and I'll have the output here. So 1, 0, it is 1. So again, one more clock pulse, it will shift towards right, and 0, 1, it is again 1. Next, again one more clock pulse, it will shift. So 1, 1, 0, so 0, 0, it will be 0. So again it will shift 0, 1, 1, so 1, 0, it will be 1. Again it will shift 1, 0, 1, and 1, 1, it will be equal to 0. 0, 1, 0, 0, 1, it will be 1. XOR with 0, 1, it will be 1. So 1, 0, 1, XOR with 1, 0, it will be 1. 1, 1, 0, XOR 0, 1, it will be equal to 1. Again, one more clock pulse, you'll have 1, 1, 1, 1, 0, XOR, it will be 1. Again, shifting 1, 1, 1, 1, 1, it will be equal to 0. Next, again one more clock pulse, this will shift towards right, so 0, 1, 1, and XOR with these two, you'll have 0. So again one more clock pulse, 0, 0, 1, and 1, 1, it will be equal to 0. Again one more clock pulse, 0, 0, 0, 0, 1, it will be equal to 1. Again one more clock pulse, 1, 0, 0, 0, 0, it will be equal to 0. Now again one more clock pulse, 0, 1, 0, 0, 0, it will be equal to 0. So this is how it will proceed. If you just observe the C3, C2, this is C3, C2, C1, C0 values. If you just observe, this is again the repetition. Whatever initial state we had, the same state we are getting one more time, 1, 0, 0, 0. This is one more time we are getting it. Okay, so that is the reason. Again it will proceed. One more clock pulse if it gets, again it will repeat. One more clock pulse it will get, again it will repeat. Okay, so from this I can say that it is a periodic sequence. Okay, so now finally let us write the complete sequence what we have got. Okay, it's nothing but 0, 0, 0, 1, 0, 0, 1, 1, 0, 1, 0, 1, 1, 1, 1. See the same thing, whatever last bit is nothing but the PN sequence. So this complete thing I'm writing. Whatever is available with C0, I'm writing the entire thing. Okay, see this entire thing I'm writing. Okay, so this is because this is nothing but the output. This is nothing but the output PN sequence. So that is the reason I have written this. Okay. So what is that? 1, 1, 1, 1, 4 ones. Next I'll have 0, 0, 0. Next again 1, 0, 0. Something like this. It will repeat. Okay. So whatever the last LSB bit I have, the same thing I've represented here. And if you observe, after this it is the repetition. So like this it will go on. Okay. So this length is nothing but this length is nothing but the PN sequence length. Okay, so the fundamental period of this PN sequence is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. N is equal to 15. Okay, and this is what the first question answer. Okay, A answer. B, he is saying that you need to take the length of sequence in one period. Okay, so it means that we can take only this much. 0, 0, 0, 1, 0, 0, 1, 1, 0, 1, 0, 1, 1, 1, 1. So this is the PN sequence in one period. One period. Okay. So this is what the PN sequence. Now coming to the third one. Third one I have already explained you. Your TH is nothing but 2 times of TS. Okay, it means that in one hop you will be transmitting 2 symbols. That is what it means. Okay. Now he is asking you to sketch the frequency versus time on x-axis and frequency on y-axis. Okay, with this you you need to assign the frequencies on y-axis, and you need to assign time period on x-axis, and you need to plot it. Okay, so how to plot, I'll just explain you once again. So what will happen, as I've already mentioned, you have die bits. Okay, MFSK transmitter, MFSK frequency, MFSK frequency 00, I'll assign as F0 to 01 F1, 1 0 F2, 1 1 F3. This is what the output. If you just take the transmitter first, the data you're giving it to the MFSK modulator. Okay, MFSK modulator. Where is this? MFSK modulator. So I'll get 4 frequencies: F0, F1, F2, F3. Okay, and from the PN sequence also I should get 8 frequencies here. Why? Because the PN sequence is segmented into 3 bits. Okay, from where I got the information, from in the question itself he has mentioned. Okay, so if you just take here, the length of the segmented PN sequence is 3. Okay, so we need to segment PN sequence into 3. So since you are taking it as 3, so PN sequence segment, I'll have 8 frequencies. Okay, so hopping carrier frequencies. Okay, so 0, 0, 0, 0, 0, 1, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. Okay, so F 0, 0, 0, let me assign the frequencies FC0, 0, 0, 1, FC1, FC2, FC3, FC4, FC5, FC6, FC7. Okay, now what will happen? We will also take the given sequence, given data sequence. What is the given data sequence? It is 1 0 0 0. This one is nothing but the given sequence. Let me write that sequence. So 1 0 0 0 1 1 0 1 0 0 0 1 1 1. That much only is given. 1 2 3 4 5 6 6 ones. 1 2 3 4 5 6 0 0 1. This is the given data. Okay, so given data we need to divide it into two bits together, because each symbol consists of 2 bits. So this is what the division here. So you know that F0 1 0 1 0 is nothing but F2. Okay, so those frequencies you need to assign here. 1 0 is F2, 0 0 is F0, 1 1 is F3, 0 1 is F1, 0 0 is F0, 0 1 is F1, 1 1 is F3, 1 1 again F3, 1 0 F2, 0 1 F1. This is what the frequencies of the given data sequence. Okay, now he has also given the, we have also obtained PN sequence. PN sequence, what we have obtained, it is nothing but 0 0 0 1 0 0 1 1 0 1 0 1 1 1 1, and again after this it will again repeat. Okay, so what is it? Okay, let me write a little more. It is 0 0 0 1 0 0 1 1 0 1 0 1 1 1 1. Again after this again it will repeat 0 0 0 1 0 0 1 1 0 1 0 1 1 1 1, like that it will go on. Okay, so now again we need to divide this into 3 bits here. Okay, because the PN segment he has given us 3 bits in each segment. Okay, so 3 bits, 3 bits like this. Now 3 bits like this. 0 0 0, it's nothing but F0. So again using this frequencies we need to allot here. Okay, 0 0 0, it is F0. 1 0 0 F4, 1 1 0 F6, 1 0 1 F5, 1 1 1 F7, F0, F4, F6, F5, F7. Okay, this is how it will be. Okay, now after this I need to take I need to draw the frequency versus time. This is the time period, and on this I'll take the frequencies. Okay, so I need to take the carrier frequencies FC1. Okay, this let me consider as FC0. This is FC0. This I'll consider as FC2, FC3, FC4, FC5, FC6, FC7. Okay, FC7. This is what the frequencies I have. Okay. Let me take different pen now. Okay, fine. Now on the time period also I will take the time slots. Let me take it as TS, 2 TS, 3 TS, 4 TS, 5 TS, 6 TS, 7 TS, 8 TS, 9 TS, 10 TS, 11 TS, like that it will go on. Okay, so and you know that each TH or TC is equal to 2 TS. It means that this is nothing but your TC. From here to here is nothing but your TC. Here to here it is nothing but TC. In each TC we need to transmit two symbols TC. From here to here again it is TC. Like that it goes on. Okay. So now let me assign the. Okay, so what are the what is the data he has given? He has given us 10. Each symbol, see, from here to here, it will occupy one symbol will occupy in this duration, right? So let me take that. Let me take different colored pen. Okay, so 0. What is the given data? 10. Here 10, 0, 0, 1, 1, 0, 1, 0, 0, 0, 1, 1, 1, 1, 1, 1, 0, 0, 1. Okay. And here one more thing is in this TC duration, I need to transmit 2 bits. Okay, and what is that TC? First I'll take as 0, 0, 0. Okay, in the first chip duration, I'll transmit these 2 bits. Second chip duration, I'll transmit 1, 0, 0 along with that 2 bits. Okay, 2 symbols, 1, 1 and 1, 0, 1. Next 1, 1, 0. Next 1, 0, 1. Next 1, 1, 1. Like that it goes on. Okay, so anyway, since I have only until 0, 1, it's fine. So whatever given data and whatever I have taken here, it's fine. Okay, 1, 0, it's nothing but F2. This is F2 frequency. 0, 0, if it is F0. 1, 1, F7. Oh, sorry, F4. Not F4, F3. We will also assign the frequencies here so that when you are plotting it, it will become easy for you. So 0, 1. See, whatever frequencies I am allotting now, it is with respect to the symbols. Okay, for this F3, for this F1, for this F0, for this F1, for this F3, this F3, for this F2, 0, 1, F1. Okay, in the same way, I will also assign the frequencies for 0, 0, 0, 0, 0, 0, FC0, 1, 0, 0, FC4, 1, 1, 0, FC6, 1, 1, 1, sorry, 1, 0, 1, FC5, 1, 1, 1, FC7. Okay, so from the tabular column only I have taken all this. Okay, now I need to plot the frequency versus time. Okay, so you know that in one symbol I need to one chip duration I need to transmit these 2 symbols. Okay, so first take here it is nothing but first one is F2 plus FC0. First one is FC plus F2 plus FC0. F2 again F2 FC0 plus F2. So it will be like, let me consider this frequency after adding FC0 with F0, this might be the value. Next F1, F2, F3. Okay, so now it is F2 plus FC0, in the sense FC plus F2. Okay, so F2 is somewhere here. So in this duration, I will be transmitting. I'll be transmitting 1, 0. Okay, in this frequency, I'll be transmitting 1, 0. So this is what F C0 plus F2. Next one is in the same period I should also transmit this symbol F0 also, F0 symbol also. So FC0 plus F0. Okay, so that is what is happening here. If you just see the transmitter, only the sum values it is taking. What is the transmitter? So when only the sum values it is taking, and it is the bandpass filter should accept only the sum value. So that is what I am drawing here. Okay, so the transmitter signal will have this frequency components. Next, F0, FC0 plus F0, FC0 plus F0. This is F0. So I'll have from here to here, I'll have this as the, in this frequency, this 00 will be transmitted. Then FC4 plus, this is nothing but FC0 plus F0. In the same way, FC4 plus F3, FC4. So FC4, so this is F0, F1, F2, F3. Okay, FC0 plus FC0 plus, FC4 plus F3. F3 somewhere here. What I'm doing, I think you people are understanding. Here what I'm doing, I'm just taking the duration so that I'll be able to draw it exactly. I'm just mentioning where exactly this will come. Okay, where exactly this will be. In the same way here. To plot the frequency band. Okay, to just draw the frequency band, I'm just taking it in this way. Okay, so now it is FC4 plus F3, FC4 plus F3. So F3 is here. So in this is the band of frequency where FC4 plus F3. Okay, then FC4 plus F1. F1 is here. FC4 plus F1. Next it is, this is how you need to proceed. Okay, FC6 plus F0. FC6 is here. So this is F plus F0 plus F1 plus F2 plus F3. Okay, so what is that? FC6 plus F3. F3. This is FC6 plus F3. Next is FC6 plus F1. F1 is here. FC6 plus F1. Next, FC5 plus F3. FC5 here. F0, F1, F2, F3. What is that? FC5 plus F3. So it will be somewhere here. FC5 plus F3, then FC5 plus F3 again. FC5 plus F3. Next is FC7 plus F2. FC7, so F0, F1, F2, F3. So FC7 plus F2. FC7 plus F2, it will be here in this duration. Okay, so this is the frequency band. FC7 plus F2. Again, FC7 plus F1. F1 is here. FC7 plus F1. Okay, so this is the frequency versus time graph for the hopping. So if you just observe here, here from here to here it is hopping, from here to here it is hopping, from here to here it is hopping. The frequencies are changing. If you just observe, the frequencies are changing in this way. So that is the reason it is said to be frequency hop spread spectrum. And why it is slow? Because within one chip duration you are transmitting two symbols. That's why it is said to be the slow frequency of spread spectrum. Okay, because in one this is only one hop. One hop you are able to send two symbols. Okay, so slowly it is hopping. Okay, from FC0 to FC4, it is hopping slowly. So that's why it is said to be slow frequency of spread spectrum. Okay, then finally, the last question. Now, this is what is transmitted. Now at the receiver. Okay, receiver, what it will do? You take the receiver block diagram. Receiver, what it has to do? It has to the received signal FJ plus FCJ, which will be given to the multiplier, so that the multiplier will be output will be like, and here we are using the same PN sequence generator with the same segment. Okay, so FCJ and this one, this and this will get added and also subtracted. Those terms will be at the output. Now I need to tune the band pass filter so that I'll get the only the difference frequency at the output. So if the receiver output at the receiver, it will despread. Okay, so at the receiver, what will happen? First, you have the same PN sequences generated 0 0 0 1 0 0 1 1 0 1 0 1, like that 1 1 1. Okay, and again it will repeat. Okay, this is FC0, FC4, FC6, FC5, FC7. Okay, FC7 it is. Okay, so what will happen here? It will, this is what the PN sequence generated. Okay, since this is the PN sequence generated, and what is receiving? The received signal frequency, the received signal frequencies, what is that? FC0. If you just take only the first one, okay, so FC0 plus F2, okay, so 0 0 0, okay, for this if you just take FC0 plus F2 minus FC0, because the band pass filter will take only the different signal, so this and this will get cancelled, so I'll get F2, and this F2 should be given to the MFSK decoder. So corresponding to this F2, it is nothing but what is that symbol? 1 0, no? 1 0. Is it 1 0? 1 0. 1 0 will be the output. This is what the estimated signal. In the same way, if I have the second one, what is that? FC4 plus FC4 plus FC4 plus F3. FC4 plus F3, then the PN sequence will provide minus FC4, so both will get cancelled, and F3 will be given to the MFSK decoder, so that it will encode 1 1 corresponding to this F3. This is how it will happen. Okay, so here again he is asking you to plot the received signal frequency versus time. So again we need to do that. This is a time. Let me just take it little big. This is the frequency. So here the frequencies are nothing but this is F0, F1, F2, F3. Okay, so in the first, let me write it as TS, 2TS, 3TS, 4TS, 5TS, 6TS, 7TS, 8TS, 9TS, 10TS. Okay, this duration should be same. Okay, so let me just take the dotted line. first duration, I should get F2 signal. F2 is nothing but 1 0 1 0. This is 0 0 1 1 0 1 0 0 0 1 1 1 1 1 1 0 0 1. Okay, so at the receiver, this will be given to the demodulator. So what will happen from 0 to TS? I should get 1 0. 1 0 corresponds to F2. From F2, this is what I'll get. Okay, then in the second duration, from here to here, it is nothing but TC. Hop duration, TC. Here to here, again it is TC. Here to here, again it is TC. Here to here, it is nothing but TC. Okay, so F2, see if in one symbol duration, in one chip duration, I need to get two symbols. So F2 I'll get, and 0 0, which is nothing but F1 I'll get. Next, 1 1, it corresponds to F3. Next, 0 1, F1. 0 0, 0 1, 1 1 again, 1 0 0 1. So this corresponds to F1, this corresponds to F2, this corresponds to F3, here also F3, here F1, F1, F0, F0, F2, F3. So this is what the frequency versus time plot for your received or dehopped signal. Okay, so this is all related to the slow frequency hop spread spectrum. Okay, so the next one is, hope this is clear to you. Hope this is clear to you, all of you.
Yes, ma'am.
Yes, ma'am.
Okay, so next I'll go with the fast frequency hop spread spectrum. Okay, so here again, as a name implies, it is fast. Okay, so RH. Okay, RH. In the previous case, it was like RS is equal to n times of RH. N times of RH. That is what we had for the what is it? Slow frequency hop spread spectrum. Slow frequency hop spread spectrum. This is how we had. Here it is reverse in the sense, in one hop, RH is equal to n times RS. Okay, RH is equal to n times RS. So here the symbol rate is more when compared to the hopping rate. Symbol rate is more when compared to hopping rate. Here the hopping rate is more when compared with symbol rate. Okay, here to understand this properly, I'll just go to the time domain. Time domain, I'll just cross multiply. So I'll have as 1 by RS, which is equal to n into 1 by RH. Okay, so 1 by RS is nothing but TS is equal to n into TH. Okay, so if you just observe here, here I'll get as TH is equal to n times of TS. It means that if I take n value as 2, okay, so in one hop I'm able to transmit two symbols. Here if you just observe, in the same way you take 2. Okay, so in 2 hops we'll be transmitting the same symbol will be transmitted 2 times. Okay, so that is what the difference. So that is the reason here the hopping is changing fastly. Okay, it is hopping faster. So that is the reason it is said to be the fast frequency hop spread spectrum. So TS is equal to NTH. Okay, so in the same way, like how we have taken the example, in the same way here also we need to take the example. Okay, so in fast FHSS, the relationship the relationship between, okay, in first one is determine the relationship between bit rate, not the symbol rate, okay, bit rate and chip rate, assuming 2 hops per MFSK symbol. Okay, so from this I will just write what he has given here. So he is saying that 2 hops, okay, 2 hops in the sense, oh, you have got other class also, no? Let me just, okay, let me write the question first. Okay, so simple, you people can copy down the question. Next, sketch the variation of frequency of transmitted sequence with time if binary sequence is 01101100 and so on, and the PN sequence is 1. Here he has given the PN sequence, you need not generate it, 100 1010 so on. Okay, it's again the repetition. Okay, this is what the second part. Third part, also sketch the dehopped MFSK signal frequency with time. Okay, so this I'll do it tomorrow. Okay, if anybody has got any doubts, you can ask me. Otherwise, I'll continue from here tomorrow. Okay, that's all for now. Thank you. Anybody have any doubts, you can ask me. Otherwise, you can leave.